Simple harmonic motion, or SHM, is a term that we use for something that's oscillating. When an object undergoes SHM, it moves through a certain path repeatedly and over specific intervals of time. So in AP Physics, the processes of SHM are most commonly represented or observed in a pendulum and a spring. So in a pendulum, if I pulled back this bob by a certain distance, then it would travel in the opposite direction that I originally pulled it back in. Then it would swing back to its original position that I pulled it back to, and it would go back and forth like this, swinging from the left to the right. Each cycle, which would be from this position going back and forth, would take the same amount of time, so simple harmonic motion is also periodic. That means that one of the ways that we can mathematically describe simple harmonic motion is through a period. So a period, which we write as t, is how long it takes for an object to complete one cycle of motion. So if the bob took 5 seconds to travel from here to there and back again, then the period would be 5 seconds. And the inverse of the period is what we call the frequency. Frequency describes how many cycles it would go through in 1 second. So if we take the inverse of 5 seconds, then the frequency would be 1/5. And this makes a lot of sense because the frequency is telling us that the pendulum bob finishes 1/5 of a cycle per second. Another quantity here is the amplitude. So the amplitude is going to be how much I pull this bob back by. So the greater the angle between the string in its rest position and its displaced position, then the greater the amplitude will also be. But what's interesting here is that no matter how much you pull the bob back by, so no matter how much you increase the amplitude, the period will always stay the same as long as the string that you're using is the same length and you're conducting the experiment on the same planet. Well, why is that? Well, it's because when we take a look at the formula for the period of a pendulum, which is t equals 2 pi times the square root of L/g. Well, the only two variables here that affect the period are L, which is the length of the string, and G, which is the gravitational constant. And remember that on Earth, the gravitational constant has a value of 9.8. So long story short, amplitude has no effect on the frequency or the period of the oscillations, only the length and the gravitational constant do. And that's interesting because we don't see a mass variable here in this equation either. So the mass of the bob at the end of the string also has no effect. If you increase the weight or the mass of this bob, then it's still going to take the same amount of time to go through each cycle. So now let's take a look at simple harmonic motion with a spring. And let's say that this spring is attached to a wall and we put a mass at the end of the spring. So when I pull back on the mass, it's going to try to go back to its original position, but then it's going to end up overshooting it and move back over to this direction by a certain amount of distance. And then it's going to come back again to the position that I pulled it back to. So just like the pendulum, it's going to go over these cycles of motion back and forth in certain periods of time. So the amplitude in this case is going to be how much I pull the mass back by. And remember how I said for the pendulum that amplitude has no effect on the period and the frequency? Well, that's going to apply to springs as well. So when we take a look at the formula for the period of a spring, it's equal to 2 pi times the square root of m/k. So here amplitude has no effect again because the only two variables in this equation are mass and the spring constant k. And remember that the spring constant is basically a measure of how stiff the spring is. So unlike the pendulum, the mass or the value of the mass at the end of the spring actually matters for when you're trying to calculate the period. So in the next video, we're going to take a look at how the energy changes when the mass at the end of the spring or the pendulum shifts and moves between these two positions.